In this video, we return to hydrogen-carbon correlation spectroscopy. As a review, the one-bond HMQC experiment focuses on one-bond carbon-hydrogen coupling constants, which are fairly large in magnitude. That means that the length of the delay between the pulse on the proton frequency and the pulse on the carbon frequency is relatively short, on the order of 3 to 4 microseconds. On the other hand, for multiple bond hydrogen-carbon correlation spectroscopy, literally heteronuclear multiple bond correlation, we're now aiming for the smaller coupling constants for 2 and 3 bond carbon-hydrogen couplings. This now leads to a relatively longer time between the pulse sequence for the hydrogen frequency and the carbon-13 pulse. This difference allows for the focus to be on the smaller coupling constants, ignoring one-bond hydrogen-carbon coupling constants. This table from the textbook focuses primarily on two-bond carbon-hydrogen bond, carbon-hydrogen coupling constants, but the three-bond carbon-hydrogen coupling constants are similar in magnitude. These are in table 4.2 of the textbook. Some additional two-bond and three-bond carbon-hydrogen coupling constants come from the book from Cruz, Rodriguez, and Jaspers, and this shows a variety of two-bond and three-bond carbon-hydrogen coupling constants. Recalling the data that we gained from the HMQC experiment, along with the connections, along with the spin systems from the COSY, proton-proton COSY spectra, we now need to determine how the spin systems are connected at G with the connection at B and with A and with carbon C. The HMBC data giving 2 and 3 bond correlations between carbon on one fragment and hydrogen on another fragment will help us combine these 4 pieces, as well as confirming the correlations that have already been determined in the COSY and HMQC spectra. It's a good idea to keep this scheme in front of you as you evaluate the HMBC spectra shown here. We'll note the correlations and bring these to another page with all of the data that we have so far to put this together. On the left, we have a table showing the one-bond HMQC correlations between carbon-13 and attached protons, along with the 2-bond and 3-bond correlations from HMBC, colored in red. In blue are 4 fragments, including the 2 spin systems established by COSY. And now we can begin putting things together. The goal is to determine how carbon G is connected with the other fragments, carbon C, carbon A, and carbon B. For that reason, we'll focus primarily on the protons that are near or at these atoms for bond connection. Let's start with proton A. Proton A shows a correlation with carbon A, carbon C, a 2-bond correlation with carbon D, which we already knew, and we see a correlation of proton A with carbon G. The problem is that we're seeing too many correlations of proton A. These could be 2-bond or 3-bond correlations. And so we need a way to distinguish between the more distant correlations. We have the same problem with protons C and E, which show a correlation to carbon A, carbon B, and carbon G. But that doesn't tell us enough about structure. Where things get more interesting is looking at protons B and D. As a digression, you'll notice that I've placed proton A and B trans to each other due to the large coupling constant noted for proton B. Getting back to the HMBC correlation, protons B and D have a 2-bond correlation with carbon B. That confirms what we already knew. We can probably pretty firmly now make this a double bond. But it also shows a correlation from proton B and D to carbon A. This must be a 3-bond correlation. And now we've completely bonded the carbons B and D with 4 bonds total. For the 6th carbon fragment, let's look at proton F. Proton F shows a correlation with carbon A. So that also must be a 3-bond coupling. The other couplings of proton F are the 2-bond couplings that we already know about with carbon F, with carbon G, and a 3-bond coupling that we already know about with carbon H. So that's confirming what we've already learned from HMQC and from COSY. Let's now redraw everything, showing the connections of carbon A with carbons B and G. We've now linked 9 out of the total 10 carbons. We just have to figure out how carbon C is connected. But A is missing a couple of bonds, as is C. So let's revisit protons C and E. If we bond carbons A and C, then it makes sense that protons C and E have a 2-bond correlation to carbon A and 3-bond correlations with carbons B and G. And that constitutes the complete structure. We can and should look at the remaining HMBC correlations to make sure that confirms what we know from HMQC and COSY, and I will leave that to you to do on your own for practice.